Hello, everyone. This video is to, no, I don't want to switch to tablet mode. What are you asking? But this video is to help you with more work and energy problems where there's multiple forces doing work. And it's the same strategy as it was for regular work energy problems, but now we got, maybe two, maybe three works, who knows? Again, suggested, if you want, draw a picture of the scenario. This is a scenario where something is pushed across a frictionless surface and then it goes along an incline, and you want to know how far it goes up the incline. So if I were to draw this out really quick, looks something like this. And there we go. That's beautiful. There is an object. It never mentions whether or not it starts from rest. In fact, it doesn't mention its initial velocity ever. By now, in this time of the year, you should know that that means the initial velocity is zero. It's implied. Don't panic. Yeah, it's zero because it doesn't even talk about it. You never even asked to solve for it. But there is a force applied, which I'm going to represent in my problem, and it's a force of 300 newtons at an angle of 15 degrees, just to get a visual of this. And that force is applied for about 10 meters. So this is going to be 10 meters here. After this, the force is no longer applied and it slides up a 20-degree incline. All right, we got an incline at 20 degrees. Terrific. 20 degrees. And there's some friction. Yippee. And we don't know how long the incline is. In fact, we're trying to solve for that. We don't know this distance. And also by now, you should know that if it's saying how far along the incline does it go, that means the final velocity is zero. If it's still moving, it hasn't reached that farthest point, silly. So it's the same thing as like, how high does it rise? Well, it comes to a stop when it reaches its highest point. Well, it comes to a stop when it reaches as far as it can up an incline. As mentioned in class and in an earlier video, even though we don't know what this height is, like we don't know what it is, we can relate it to the hypotenuse and the angle, which is d sine 20. Don't panic. The height is distance sine 20. It's okay. You don't need a number. That's what it is. Relax. All right. As per the last time, you want to write out the work energy theorem. We start with a little kinetic energy in the beginning, a little potential energy due to gravity, a little work, a little kinetic energy final, and potential energy due to gravity final. Terrific. Same questions. Is it moving in the beginning? Yes or no? Well, no. I've even labeled it in my picture because my picture is that amazing. Is it above height zero? I'm going to go with no, although not labeled in my picture. I'm implying that the lowest part of my story is in fact height equals zero. So I'm going to cross that off. Bloop. Are there forces doing work to change the energy? Yeah, there's a 300 Newton force that's applied. It's going to actually increase its speed and change its kinetic energy. There's also friction, which is going to try to slow it down and decrease its kinetic energy as it rises and gains potential energy. So there's actually two things doing work. Oh my goodness. And I'm just going to write this here. The kinetic coefficient of friction is 0.4. Is it moving in the end? No, because I said so. And is it above height zero in the end? Yeah, because it's above where I defined height zero. So here's the deal. There are two things doing work. There is, I'm going to take my time with this so you can see it. There's the work done by the 300 Newton force, and there's the work done by the force of friction. I'm going to take my time to write this out. Remember, work is FD cosine theta, right? Work equals F delta D cosine theta. All right. Well, for this one, that's pretty easy. That's 300 newtons applied for a distance of 10 meters at an angle of 15 degrees. The angle between the force and the direction of motion is 15 degrees, that's all. As in previous problems, we've talked about the work done by friction. The work done by friction, you can write it out as, remember, it's the force. I'm going to take my time with this one more time just for this video. Force of friction acting for a distance. The angle between the force of friction and the direction it's moving is 180 degrees. It's moving up and to the right, friction acts down and to the left. That's -1. If you want to make the work done by friction negative without writing cosine 180, that's cool. Just start off with negative force of friction, which is mu Fn. Don't forget the delta D. On an incline, the normal force is equal to the force of gravity in the y direction, or FGy, which is mg cosine theta. Don't lose the delta d. So I have two works here, okay? And then afterwards, there is the potential energy. But I'm just highlighting, writing out the two works here first. Let me rewrite them, so it's a little bit neater. We have 300 newtons acting at a distance at an angle of 15 degrees, minus the coefficient of friction, which is 0.4, the work done by friction, 40 kilograms, 9.8 meters per second squared. The angle of the incline is 20 degrees, but I don't know the length of the incline. That's not good, but I'll leave it there. It's okay. On the right side, we have the potential energy due to gravity, which I didn't write here. I apologize. That's just mgh. Well, we have 40 kilograms running out of space, 9.8 meters per second squared. I don't know what h is, but I do know it's delta d sine 20, which I squeeze in there. And it's okay. We're solving for that distance. And now what I've got going on here is a beautiful equation. Please don't solve this in one step. Please, right? Take your time. Okay, the 300 times 10 cosine 15, that turns out to be 2898 joules. This whole shebang-a-bang here, multiplied by delta D, you get 147 newtons times the distance. On the right, 40, like some people panic here, 40 times 9.8, but then there's a delta D and a sine 20. What do I do? 2 times 3 times 4 is the same as 4 times 3 times 2. Who cares? Just do 40 times 9.8 times sine 20 times delta D, and you will get 134 newtons times the distance. Now, we can combine like terms here. 2898 joules equals, I did not write this down, but I am confident I can do 181 newtons delta D. Solving for distance, I think I get 10.3 meters. And that's it. That is it. Let's review this really quick. I mean, once we got here, it's just doing math. So basic strategy is it stays the same. You know, what we did in class. We draw a picture, we label heights of 0. If it's an inclined plane, why is it jumping around so much? Come on, buddy. Come on. There we go. If it's above height, I would label the initial and final velocities, the heights of 0. If it's an incline, I'd immediately write delta D sine theta. If I could solve for anything, I will. Otherwise, I'll just write an expression. You know, get organized. Then you write out your work energy theorem. Just as before, we cross off the things that we know and the things we don't know. And then work. You know, take your time, write them all out. There could be the work done by friction, which we had in this problem, the work done by an applied force, which we had in this problem. Or there could be a rope, you know, like whatever it is. We could have a problem with 3 works, which I believe somewhere in your homework packet you probably do. Just write each one out and sub in the math for each work. Some people prefer option 2 here, which is to write out the works on the side, like somewhere off the side, and that's okay. It's your way of getting organized. I wrote it out in like one equation. And some people will be like, well, I can calculate the work done by friction and get a number. So they do that on the side. And they can calculate the work done by the applied force, and they do that on the side. And then they bring those numbers back into the equation. I don't care. It's how you see it best. You can still solve. There's no perfect way to do it. It's what works for you. But that's it. It's not a big deal. If there's multiple works, multiple forces doing work, then you have multiple works. Anyway, I hope that was helpful. And that's about it. This was a decent one. I'd give it 3 out of 5 stars. Still wouldn't change a thing.